Thank you very much for giving me the opportunity to present our works here. I will talk about average model for plasma physics. Especially, I will focus on averaging collisions kernel. For example, Fokker-Planck Landau kernel. And this part is a joint work with my PhD student, Céline. So the main motivations concern the transport of charged particles under strong magnetic field, so it's related to the magnetic confinement fusion. I will use kinetic description, but I will take into account the collisions. So here is the main equation, Landau equation. So you have the transport part with a high magnetic field, and we'll take into account the collisions using collision kernels. And the collision kernel we are interested in is the Fokker-Planck Landau bilinear collision kernel. So as usual, the function f denotes the presence density of the particle inside the phase space. And we want to pass to the limit when epsilon is very small, meaning that the magnetic field is very high. So we want to see what is the limit model of this Landau equation for high magnetic field. So we have a multi-scale problem. For example, the small parameter is the ratio between the observation time and between the cyclotronic period and the observation time. So we have to use homogenization techniques. There are several methods. For example, we can use the notion of two-scale convergence. We can use also the averaging methods. The physicists call the gyro-average methods. We have to treat the oscillations. So this implies numerical instabilities, and we like to smooth out the fluctuations in order to get only the leading order terms. And the main point will be how to average the Fokker-Planck Landau kernel for the collisions. Eventually, we can derive fluid models for strongly magnetized plasma, and the same method applies for studying other interesting problems like strongly anisotropic diffusion, which is another important point for tokamak plasmas. So some references. There are a lot of papers in the literature giving approximation for the average collision kernels, but some of these average collision kernels missed the usual conservations like mass, momentum, kinetic energy. I remember here the papers by Shu and Rosenbluth. They get linearization around the equilibria, but the implementation seems very hard. There are also the papers by Xavier, Brizard, and Am using a variational approach. So what we want to do is to explain, for example, the perpendicular diffusion in space. So in the Fokker-Planck Landau kernel, you have diffusion in velocity, but we know that after averaging with respect to the fast cyclotronic motion, we'll get also diffusion with respect to the perpendicular direction. So we like to see exactly how does it work. So we like also to write the H theorem, which will allow us to write the equilibria for the average kernel. So here are some other references for the transport averaging. So the papers by Emmanuel and Eric, Gaulle, Saint-Raymond, Gendry, Auré, nourrit et un quantum. So I will start with scaling. So I'm interested in a finite Larmor radius regime. So in order to simplify the computations, I will take a uniform magnetic field, so which is very high. So this is the meaning of this small parameter epsilon here. And the idea is that the fluctuation of the presence density are at the scale in the perpendicular direction is much smaller than the scale in the parallel direction. Actually, the scale in the perpendicular direction is related to the Larmor radius, which is very small, which is like epsilon, going from which comes from this scaling of the magnetic field. So let me introduce some notation. So the perpendicular direction are x bar. The perpendicular velocity is v bar, and this is just the rotation of the velocity in the plane orthogonal to b, rotation of angle minus p over 2. So after all these scalings, the Landau equation becomes like that. So just a transport equation with a collision term. And in the transport equation, you have a dominant transport field, which is this one plus this one. And you have another advection field, let's say, of order 1. So if we want to simplify the notations, we can denote by T this dominating transport operator. And the other advection field is denoted by A. And in this case, the Landau equation can be written like that. So we have a transport part with a dominant field and another field of order 1, and we have to take also into account the collisions. So since we have this higher frequency coming from the cyclotronic frequency, probably we'll have to deal with a fast time variable denoted by S, which is equal to the slow time variable divided by epsilon. So this is the point we have to deal with two time variables. So we can go through the two-scale convergence approach. Another possibility is to use just an ansatz, just write the presence density as a combination of a dominant part plus fluctuations at the scale epsilon plus another correction at the scale epsilon 2 and so on. We can plug in this ansatz into our Landau equation. And at the leading order term, you get this constraint, meaning that when epsilon is very small, this part should vanish, which is exactly this dominant operator T. And at the next order, we get an evolution equation for the dominant density F, but with this Lagrange multiplier, which is the first correction F1. So it's a very standard problem, how to eliminate a Lagrange multiplier. Now, and we know that at any time t, the function f satisfies this constraint. So we need a closure for this equation in order to find a model, a limit model for the dominant term f. And we expect that the limit model will be a similar equation. It means we have a transport part with another advection field here, and here we have another collision kernel. So we want to see how we can compute this new advection field and this new collision kernel. So let's detail a little bit more what exactly is this constraint. So it's just transport operator, so we can associate the characteristic flow And saying that f satisfies a constant, it's exactly saying that the function f remains constant along the characteristic flow. Since we choose an uniform magnetic field, we have explicit formula for these characteristics. The flow is periodic. And these are the invariants, which are exactly the center of the Larmor circle, the parallel position and velocity, and the radius of the Larmor circle, which is exactly the modulus of the perpendicular velocity. So the point is now to give another formula for computing the projection. And for example, we can use averaging. So the definition for the average operator will be, for example, for any function u in a Lebesgue space, let's say L2 in x and v. I take a point x and v. I construct the trajectory starting for x and v. As I said before, the trajectory is periodic. So here you have the formula, the explicit formula of the trajectories in this particular case with a uniform magnetic field. And just take the average over one cyclotronic period of this function u along the flow. And this will be the definition of the average operator. And you can prove that this average operator coincides with a projection onto the kernel of T. So this is not very hard to see because it is easily seen that the computation here depends only on the trajectories, but not on the particular point of the trajectory. So it's something which depends only on the invariance of the trajectory. So it's something in the kernel of T. And we can check this variational approach, saying that this quantity is exactly the orthogonal projection onto the kernel of T. So we have a formula for computing projection, orthogonal projection onto the kernel of T. Now we'll use this formula, and the point is to compute commutators between transport and the average operator, because now I can replace the projection by the average operator, and if I manage to find a formula saying how transport operator is commuting with average, I can simplify this limit model. So the next point will be how to compute commutator between the advection and averaging. So we intend to start with average of some transport and perform some computations, and at the end to find another transport of the average of f, but f satisfies a constant, meaning that f is constant along the flow. So when taking the average along the same flow, it will be unchanged. So you will get this formula, and we'll try to find explicit formula of these components of the new advection field with respect to the initial advection field. So there are some computations here. The point is that the computations simplify a lot if we pick adapted coordinates. So the good coordinates will be exactly the invariance of the flow. So the center of the Larmor circle, the radius of the Larmor circle, and so on. And actually, it's exactly what is done by physicists, because they replace present density of the particle by the present density of the Larmor circle for using this well-adapted system of coordinates. So at the end, changing the coordinates means also to choose special derivations, the derivation with respect to this new coordinate. And the main point is that with respect to this new coordinates, so in respect to these new derivations, all these derivations are commuting with the average operator. So this is why it's very simple to perform computations in this new system of coordinates. More generally, anytime you take vector field in involution with vector field B, the derivation along C is commuting with averaging operator along the flow of B. So it's very easy to perform computations using this new system of coordinates. And at the end, you get a formula saying how average and divergence are commuting. So you take a general vector field and at the end, so at the you start with taking the average of the divergence, and at the end you get the divergence of something else, where the new the components of the new advection field are expressed in terms of some averages with respect to the components of the original magnetic field. So now we know how to average first order differential operators, but inside the Fokker-Planck Landau kernel we have both diffusion operator with respect to velocity, and we have also convolutions with respect to velocity. So probably we will manage to average the second order operators, but I don't know for the moment how to average the convolutions in velocity. So a good starting point it will be to consider first very simple kernel, which is called relaxation operator, Boltzmann linear relaxation operator, just convolution in velocity, and try to see what the average could be of this kind of operator. And the final result is here. So just consider a convolution in velocity, and under some hypothesis, we get this formula. So the average of this convolution is another convolution. But now you have to integrate not only in velocity, but also with respect to the perpendicular directions. And we can compute the new cross-section, which will be the original cross-section multiplied by this probability measure. Maybe a comment about this probability measure. So let me recall the notation for this variable. So R prime are the radius, so the modulus of the perpendicular velocity. V3 is parallel velocity, and this new variable is just this one, which is related to the distance between the center of the Larmor circles. So if you take a look at this probability measure with respect to this variable, this is a characteristic function for these quantities, saying that we get collisions between two Larmor circles if and only if the circles have non-empty intersections. And this is very easy to understand, because if you want to perform a collision between two things, it should have the same position in space. So you need an intersection point. Okay, so we know how to average convolutions in velocity. So it's no more local in space, because now we have to integrate also in space. We can prove the conservation properties, and actually we get convolution not only with respect to velocity, but also with respect to the center of the Larmor circle. Now, in order to see how we can average second order differential operators, so just consider the Fokker-Planck kernel, which is just diffusion with respect to velocity. So at the beginning we have this diffusion matrix, and if we perform the computation as before, using the special system of adapted coordinates, using the commutation property with the averaging operator and so on, at the end we get that the average operator, Fokker-Planck kernel, it's another Fokker-Planck operator, but this time we have diffusion not only in velocity, but also in space. More exactly, diffusion in x1 and x2, the perpendicular directions. And we can compute the new, the average, the effective, we can compute the diffusion metric of the effective Fokker-Planck kernel. Okay, so now we try to combine all these results. So to put together into the Fokker-Planck Landau kernel, so we have convolution in velocity and diffusion in velocity. So we know that this kernel conserves the mass, momentum, kinetic energy, and we have also an entropy and entropy production. The entropy is the usual F log F. So we'll try to average this operator, and at the end, we like to preserve all these properties. So we can split the operator in two parts, this one with plus and this one with minus. And we compute separately the average for both of them. And the final result is something like that. So after averaging, we have a similar structure. But now we have convolution not only in velocity, but also in the perpendicular directions. And we have also diffusion, not only in velocity, but also in respect to the perpendicular directions. So here you have the matrix A plus, A minus, which gives a diffusion metric for this new kernels. And there are some special forms for these matrices, like tensorial product, and this will be very, very useful if we want to establish a H-type theorem for the effective Fokker-Planck Landau kernel. And okay, here you have the formula for all these fields, which are a little bit complicated, but everything is completely explicit, so there is no problem to use these expressions. And as I said before, we can prove an average type theorem for this new average Fokker-Planck kernel. So as usual, you start with a weak formulation for this average operator. So just pick a test function and compute the integral of this test function against the average Fokker-Planck Landau kernel. Perform all the standard arguments, meaning that you want to use a symmetry between V and V prime, and also you want to use the symmetry when reversing the collision. So you may replace the pre-collisional quantities by the post-collisional quantities. So it's exactly the same proof. And at the end, you get this structure. So the main point here is that if you pick as test function the log function, this expression becomes exactly this one. So if you search for an equilibrium of the average Fokker-Planck kernel, this one should be 0. So all the square here should be 0. So you get a necessary and sufficient condition, a characterization for the equilibrium of the average Fokker-Planck kernel. So in particular, you have this entropy inequality, and you have the expression for the equilibria of the average Fokker-Planck Landau kernel. You also can compute the collision invariance for this average Fokker-Planck Landau kernel. So collision invariants are the function phi such that for any presence density function f, you have this quantity equals to 0. And using the weak formulation, it's clear that any phi is a collision invariance if and only if all these quantities are 0. So you have a characterization of the collision invariance, and you can compute them, and you'll get 1, which is a number of particles. These are the coordinates of the center of the Larmor circle. You have also the parallel velocity. You have the kinetic energy, and here you have a special new one collision invariance for this average Fokker-Planck Landau kernel. And this will have an important consequence when you try to parameterize, when you try to write the manifolds of the equilibria for this average kernel. This can be done by using not only 5 numbers, as for the standard Fokker-Planck Landau kernel, but 6, because here you have 6 collision invariants here. So this is a special form of the equilibria. So you have a special density here, and the mean velocity is given here, and temperature is theta, depending only on the parallel direction, and you can check that the density is maximal exactly at the mean Larmor center. So this average Fokker-Planck Landau kernel, it's a little bit more complicated than the original Fokker-Planck kernel, because now you have to integrate in 5D. So probably it's not so easy to implement this new kernel. Nevertheless, you can linearize around the equilibria, because now the main point is that we know what exactly are the equilibria. And you can prove that the new the operator obtained by linearization has exactly the same equilibria, the same collision invariance, and so on. Something about parametrization. So we can parameterize the equilibria using not 5 moments, but 6 moments. So density, this is something related to the mean Larmor circle center and mean parallel velocity. This is related to the kinetic energy, and this is related to some to the new collision invariance. And we'll get a new temperature coming from this new invariance. If we want to write fluid models around equilibria, assuming that we have a lot of collisions, for this average Fokker-Planck Landau kernel, so just use moment methods. So when this parameter is very small, we can search for a solution having a dominant part plus a fluctuation of the scale 2. And F is an equilibrium for the average Fokker-Planck Landau kernel, so we know what is the profile of this density. So be careful here, the profile is in x1, x2, and velocity, and the coefficients will depend only on time and x3. So when testing with all these collision invariants in this equation, in order to get rid of the collisions, we'll get 6 equations for the moments, which are functions depending only on t and x3. So it's a system of conservation law. So we have 6 equations, but in 1D. And we have also an entropy for this system of conservation laws coming, as usual, by the entropy F log F. Okay, so this was for the how to average Fokker-Planck Landau kernel. So now I'll try to give some details how we can use the same method in order to treat another interesting problem, which is related to the anisotropic diffusion. So, for example, inside a At tokamak, we know that the diffusion coefficients are very different along the magnetic field lines or along the perpendicular directions. There are some other applications like image processing, edge detection, porous media, and so on. So I took here a model problem, so just a parabolic equation. The matrix D is symmetric, positive, and here I put perturbations, very big diffusion in the direction of the vector field B. So the vector field B here should be related to the direction of the magnetic field. And of course, if we want to perform a numerical simulation by using explicit method, you should satisfy the stability condition. So you are obliged to take a very small time step. So this is not good for numerics. So one possibility is to try to understand at the theoretical level what is the limit of this model and solve directly the limit without any epsilon. So you can use explicit method for the limit model. So what is the starting point? If you pass to the limit, obviously the limit of U epsilon will enter the kernel of this dominant diffusion operator. And if the field B is divergence free, actually here you have second iteration of the advection along B. So the kernel will be exactly the same. So the constraint will be exactly the same. It's just function which are left invariant along the flow of B. So probably we can use the same framework. We can use the average operator along the characteristic flow of this field. Another point is the following. So we have to take a look at this commutator. So between transport and diffusion. Why? Because if this commutator is 0, we can prove that the second order operator and the average operator are commuting exactly as in the previous case. And now, if you take the average of this equation, you can get rid of this one because it's 0. And now, you can put the average inside the diffusion operator by the commutation property. And you'll get this model. So now it's very clear how you can pass to the limit in this model. And the conclusion is that the effective matrix is the same, the matrix D in this case, when the diffusion is commuting with transport. So probably what we have to do is to commute this commutator in detail. And the result is given here for any matrix field A. The commutator between transport and diffusion is another diffusion operator. And this new matrix field here is given by this expression. So this bracket between B and A is another matrix field. Now you can characterize what are exactly the matrix field such as transport is commuting with diffusion. And you get this, let's say, simple formula. So here, Y is exactly the flow of B. So you have commutation properties if and only if you have this one, which is equivalent to this one. And here you can recognize a unitary C0 group. And saying that A is such that the diffusion is commuting with B is saying that the matrix field A is left invariant along this group. And we can see this bracket as an infinitesimal generator of this group. So this is one of the main points. You can give this interpretation of this bracket, and you have to fix the functional framework. So you choose L2 weighted space with this scalar product, and you have some hypothesis how to pick the weight. And inside this framework, this operator, which is exactly the bracket, becomes Q-adjoint on the weighted L2 space. And of course, the kernel is given exactly by the field matrix, which such that the transport is commuting with the diffusion. And the important thing is that the average matrix field corresponding to D appears as the long time limit of the solution of this parabolic model. So you take this model with the initial condition D, and the long time limit for this solution is exactly the effective matrix field, the average of D. Okay, so this is explained here. And at the end, you have another characterization for this effective matrix, which is completely algebraic. So you can compute this average matrix, diffusion matrix, just imposing this condition for any function u and v satisfying the constraints. So if you know a complete family of invariants, you can compute the effective matrix by solving for this linear system. So this is the first order approximation theorem. So just denote by U epsilon the solution for the perturbed problem. U is the solution of the average parabolic problem with the effective diffusion matrix. And you have this at least weak convergence of the perturbed solution towards the solution of the limit problem. And now, in the last moment of my talk, I will present also some results concerning the Boltzmann kernel. So we'll see we can still use a technique of the averaging operator in order to compute the effective Boltzmann kernel under high magnetic fields. So the problem is how to study beams with optical axis, what is called paraxial approximation. So we suppose that the particles remain close to an optical axis, so the perpendicular velocity are very small, and the parallel velocity, the kinetic energy in the parallel direction is nearly the same. And now I assume also that we have a strongly magnetic field, and I would like to take also into account the collisions through a collision mechanism of type Boltzmann, bilinear Boltzmann kernel. So this is a beginning, the model of the beginning. So just perform the scaling. So as I said, the velocity in the perpendicular direction is small, like epsilon. You have mean parallel velocity, which is u3. And you have also a magnetic field, which is high, like 1/epsilon. And in this case, since the perpendicular velocity is small, like epsilon, and the magnetic field is like 1/epsilon, the Larmor radius is like epsilon square. So this is why here I will take the scale in the perpendicular direction like epsilon 2. So it's a finite Larmor radius regime, as before. So I remember here the Boltzmann operator, and after the scaling, I will get this formula. And in order to simplify the computation, just take gamma equals to 0, meaning that we consider the Maxwell molecule case. So after scaling, at least for the Maxwell molecule case, we get this dimensionless equation. So we have the transport part, which is the same as before. And here I have to put the Boltzmann kernel. So we need to average both the transport part and the collision part. For the transport part, it's already done. So what we can do for the collision, how we can compute the average of the Boltzmann kernel. So what is the effective Boltzmann kernel after taking into account the fast cyclotronic motion. So let me split the Boltzmann kernel into the gain and loss part. And let me remember also this probability density. This is the same as before. Averaging the loss part is not so difficult because we expect a similar structure, so just an integral operator with respect to the pre-collisional quantities. So here we have velocity, but after computation, you get not only velocity, but this new variable, which is given by the center of the Larmor circle and the parallel velocity. But the difficult point is how to average the other part. So for the loss part, we have similar structure, but for the gain part, we have to write what is exactly a collision between particles, and we have to integrate with respect to the post-collisional quantities. So the computation are a little bit complicated, but what you can imagine is just things that we have to make a collision between two Larmor circles. So what we can do, thanks to this probability density, so probably we'll have collision only between Larmor circles having a non-empty intersection. And once we have a pair of Larmor circles, just look at one of the intersection points, take the velocity at this intersection point, and in this point you can perform a standard Boltzmann collision. So you have to change the velocity in this intersection point, and with this modified velocity you can construct new Larmor circles passing through the intersection point with the post-collisional velocities. So this is a geometrical interpretation of the collision between two Larmor circles, and now you can compute everything. You get formula. Okay, so you can compute these collisions. So you'll get the expression for this the average of the gain part is a similar structure. You have to integrate with respect to the post-collisional quantities. And now just take a deeper look of the collisions between pairs of Larmor circles. What are the conservations? So we can check easily that you have conservation for the Larmor center and parallel velocity. You have the conservation for the kinetic energy, and you have also the conservation for the last collision invariant we have seen in the first part for the Fokker-Planck Landau kernel. So it's exactly the same quantities. So you can establish H theorem for this average Boltzmann kernel, starting by weak formulations of peak test function, and performs the standard arguments using Fubini, the symmetry, reversing the collision, and so on. You can prove this inequality, and you can characterize the equilibria for the new average Boltzmann kernel. And if you want, you can write fluid models exactly as before, using the method of the moments. So some conclusions. So using the average operator is possible to give exact formula for the average collision kernel. So it was done for the Fokker-Planck Landau kernel. You can do it for the Boltzmann kernel as well. So they are exact computations. So you preserve all the cancellations. So for the mass, momentum, kinetic energy, you can establish edge theorem. So this is very useful for computing the profile of the equilibria. If you want, you can write fluid models around this kinetic equilibria. Just use the moment method, because you know exactly what are the collision invariant and what are the profile of the gyrokinetic equilibria. Some other perspectives. So all these computations were done using uniform magnetic fields. So why this is important? When taking uniform magnetic field, you can explicit the flow along the dominant operator, and this flow is periodic, and it's very easy to write down the average operator to replace the projection onto the kernel of the dominant operator, the projection onto the space of constraint. So it will be very interesting to generalize this kind of computation, but I think it's not so easy. So at least for some special form of special shape of magnetic field, which are used in the magnetic confinement. For the moment, I'm considering only the linear problem. So the magnetic field is the exterior is given, and the electric field is also given. We should try to couple these computations with equation for the electric and magnetic field. And we can use the same idea in order to get numerical methods. So the idea is to split, let's say, the numerical solution between a dominant part, which will be the average, and the other part, which is a fluctuation around the average. And so we can use all this theoretical result in order to split between the two parts and replace the equation by a system of two equations with respect to the average and the fluctuation. And what we have to do is to use implicit method for the fluctuation, or to compute explicitly the fluctuation, and to use let's say explicit method for the average. So I will stop here. Thank you very much.